Welcome back to The Explainer. Today, we're diving into something really mind-bending. We are bringing that cosmic curiosity to the truly fascinating physics of perfect unpredictability. We're going to explore exactly how scientists are taking the beautiful, fundamental chaos of the universe and, believe it or not, using it to secure our entire digital world.
So, can we ever create true, perfect randomness? It's one of those questions that sounds super simple, right? But it actually challenges our whole understanding of reality. Think about it. Is it physically possible to roll a truly perfect die or flip a perfectly random coin? Well, if you know the exact weight of the coin, the force of the flip, the air resistance, the distance to the floor, you could technically predict the outcome every single time. It's not actually random. We just don't have enough data on hand to predict it. So where do we actually find true randomness?
Well, for a long time, the greatest minds in physics thought the universe was completely deterministic. Albert Einstein famously threw a philosophical flag on the weirdness of quantum mechanics, stating, "God does not play dice with the universe." He really believed there were just hidden variables out there that we couldn't see yet. But here's the incredible plot twist for today's explainer. Modern quantum mechanics actually proved Einstein wrong. The universe does play dice, and we are finally learning how to read those cosmic rolls.
Here's our roadmap for today. First, we'll look at the perfect coin flip, then the quantum entropy solution. Third, fixing flawed quantum machines. Fourth, the public randomness beacon. And finally, securing our digital future.
All right, let's jump right into Section 1, the perfect coin flip.
Now look at the stark contrast here between these two concepts. You've got classical pseudo-randomness, which is what our everyday computers use. They rely on these massive, complex mathematical algorithms to spit out numbers that look random, but they're always tied to an initial seed value, like the exact microsecond on a computer's internal clock. If a hacker gets their hands on that seed and the algorithm, they can literally predict every single random number that pops out. On the flip side, we have quantum randomness. This taps into the gorgeous underlying physics of quantum mechanics, things like vacuum fluctuations or the probabilistic behavior of photons. These events are fundamentally indeterminate. Honestly, even if you had infinite computing power, they are completely impossible to predict.
Which brings us to Section 2, the quantum entropy solution. So how do we capture this? What you're seeing here is a photon source shooting single particles of light right at a beam splitter. The moment that photon hits the splitter, the universe is quite literally forced to make a choice. Will it pass straight through to detector 0, or will it reflect over to detector 1? According to quantum mechanics, until you actually measure it, that photon exists in a superposition, meaning it's taking both paths at exactly the same time. The final result is a completely unpredictable binary choice. It is a true cosmic coin flip.
But here is the catch. While the underlying theory is flawless, the real world, well, it never is. Physical hardware has totally normal constraints. Photon emission rates can drift. Detectors might register false hits, which physicists call dark counts. Plus, thermal drift and environmental noise can sneak these subtle hidden biases into the system. Over time, your supposedly perfect quantum coin might start landing on heads, say 51% of the time instead of 50. And in the high-stakes world of cryptography, a 1% bias is an absolute deal-breaker. It's a gaping vulnerability.
Moving right along to Section 3, fixing flawed quantum machines.
Just look at the crazy difference here. Researchers used a picture of a sheep to test out their encryption. With the image encrypted using ordinary, slightly biased randomness, you can still totally make out the outline and shape of the sheep. The pattern is still predictable. But when they applied their newly certified perfect randomness, the image gets completely obliterated into pure, unreadable static noise. It becomes mathematically impossible to pull that sheep out of the static.
They achieve this total obliteration through an absolutely brilliant process called randomness amplification. And it's so clever. Instead of trying to build some physically flawless, impossible machine, they deliberately started with flawed, imperfect randomness, knowing full well it had biases. Then they used a special algorithm relying on quantum measurements to basically purify it. They distilled that imperfect randomness down into something physically certified as perfectly unpredictable, no matter how much raw computing power an attacker might throw at it.
The engineering behind this ETH-Zirc experiment is just staggering. They took two superconducting chips, acting as our two qubits, and stuck them in an ultra-cold environment, right near absolute zero. Then, they connected those chips using a 30-meter-long tube. By zipping microwave photons back and forth, they generated quantum entanglement between the chips. Now that 30-meter distance, that's the real magic trick. It means that when they measure one chip, the entangled response on the other happens instantly, We're talking so fast that absolutely no hidden information could possibly be exchanged between them, not even at the speed of light. This completely guarantees the result is perfectly, unassailably random. It's basically acting like an atomic clock, but for pure unpredictability.
Let's hit Section 4, the Public Randomness Beacon.
So think of the Colorado University Randomness Beacon, or CURB, which they run in partnership with NIST, as this high-tech factory. Step 1, it generates pairs of entangled photons. Step 2, it measures their polarizations an astonishing 250,000 times every single second. And finally, Step 3, it leverages a novel quantum-compatible blockchain tech called the Twine protocol. This hashes the data, slapping a digital fingerprint on it to ensure these random numbers are completely traceable, verifiable, and protected from manipulation, right before broadcasting them to the public every single day.
This quote from NIST physicist Christopher Schaum really nails the profound shift we're seeing here. We've taken this century-old philosophical debate between Einstein and our beloved pioneers of quantum mechanics, and we've actually turned it into a highly practical, cutting-edge public utility. We are quite literally taking the dice that the universe rolls and broadcasting those beautifully chaotic results straight over the internet.
Let's bring it all home with Section 5, Securing Our Digital Future. 71,313. That is the exact number of secure entropy bits, meaning units of pure, unhackable randomness generated during a massive recent experiment by JP Morgan and Quantinuum. They essentially used a 56-qubit trapped ion quantum computer as an untrusted server. When they sent it quantum circuits to execute, it took the quantum computer about 2 seconds to spit out these insanely complex random probability distributions. If you tried to force the world's largest supercomputer to do that exact same task, it would take 100 seconds. This proved, beyond a doubt, that they could generate certified quantum randomness capable of fending off simulated attacks from the most powerful classical computers on Earth.
So why does all this matter? Well, the main takeaway here is that harnessing the universe's unpredictability is so much more than just a fun physics trick for a lab. It is the absolute bedrock for securing our modern society. We're talking about quantum key distribution for unbreakable encryption, completely unhackable digital identities, totally unbiased public lotteries and jury selections, and heavily tamper-proof blockchain consensus mechanisms. Certified randomness is how we ensure that as quantum computers get more and more powerful, our security protocols can actually evolve right alongside them, keeping us a step ahead.
We have seen how scientists are capturing the probabilistic nature of photons to create the ultimate dice roll, turning classical vulnerabilities into legitimate quantum fortresses. But honestly, this is just the dawn of the quantum era. It leaves us with this really provocative thought. If the universe is fundamentally unpredictable, and human imagination has finally figured out how to bottle up that gorgeous chaos, what other invisible forces of the cosmos might we harness next to secure our future? Thanks so much for joining me on this explainer, and remember to keep questioning the universe.